Let's work an example problem of horizontal projectile motion. So the problem is the ball is thrown horizontally from the edge of a cliff at 14 meters per second. It lands 35 meters from the base of the cliff. How tall is the cliff? I like to start things with a picture. So I've got my cliff. It's some meters high, y, and there's a ball that's thrown from the top of it. And the ball is thrown horizontally to the right at 14 meters per second. Now, a free body diagram shows me all the forces. There's only one force acting on the ball. It's the force due to gravity. Yes, there was a force required to throw it, but now that it's been released, the only force acting on it is gravity. The other piece of information I know is that the ball ends up on the ground down here, 35 meters from the base of the cliff. So we're supposed to figure out how tall the cliff is, which is a little bit interesting because we don't have any information in the y direction, or at least it doesn't look like it. But if we dig a little bit deeper, we do have some information, x and y. Remember, these are independent of each other, so we should keep them independent. What I know is the initial velocity in x is 14 meters per second. Okay? It also says that the ball is thrown horizontally, and that indicates that it's not moving in the vertical direction at all, which means my initial velocity in y is equal to 0. So I do know some information in y. The acceleration in x, well, I know the acceleration in x is 0 because there's no forces acting in the x direction. There's no acceleration in the x direction. But the acceleration in the y direction is the acceleration due to gravity, which is negative 9.8 meters per second since it is pulling it down. I know how far this thing went in the x direction. Delta x is 35 meters. I do not know how far it went in the y direction. Delta y is unknown. But if I can figure that out, then the problem will be done. So let's take a look and see if I can use this information to get y direction or y stuff. Okay, we were supposed to figure out how high it goes. So in the y direction, I know an initial velocity, I know an acceleration, and I want to know a change in y. I do have the equation delta y equals 1/2 at squared plus v naught t. If we take a look at that, we can see that I can find delta y if I know acceleration, initial velocity, and time. Well, I have initial velocity and acceleration. I don't have time, so that's two unknowns. So I'm stuck right here because I don't have enough information to get time. Now, there's another equation that would allow me to get a change in position. That's v squared equals v naught squared plus twice the acceleration times the change in position. The problem is I don't know the final velocity. A lot of times people want to say the final velocity is 0, but it's not. When the ball hits the ground down here, it's actually moving. When it hits the ground, after it hits the ground is when it stops. So we do not use a final velocity of 0 for something that's falling towards the ground because that's after it hits, not when it hits. So I can't use this equation either because I don't know final velocity, I don't know change in position, so again I have two unknowns. So that means I need to use another equation and find another thing so that I can get time. Well, let's go to the x direction. The x direction says we have a change in position, we have an initial velocity. So I'm going to use the same equation. Delta x equals 1/2 at squared plus v naught t. However, I know the acceleration is 0. I know the change in position is 14 meters, and I know the initial velocity is, the change in position is 35 meters, and I know the initial velocity, which is also the entire velocity, is 14 meters per second. So I have 35 equals 14t, which means I can find t, divide by 14, divide by 14, and t is 2.5 seconds. Now, since it had the same amount of time to move horizontally as it did vertically, since the ball actually followed this path, right, it had the same time here as over in the y direction. So I can actually use this time over here. It's the one commonality between the x and y motions. So time is 2.5 seconds. So if I go ahead and substitute that in, I have 1/2 times negative 9.8 times 2.5 squared plus 0. So this is negative 4.9 times 6.25, which is about 30.625 meters. And now it is technically negative 30.625 meters because I found its change in position, and the ball did change in position and negative displacement. but that means it started with a positive initial position. So my initial position, or the height of the cliff, is 30.625 meters. Okay, so the trick to doing these problems is to keep your x and y separate from each other, keep them independent, but remember that the time in the x direction and the time in the y direction are the same. Also, don't make the mistake of trying to make your final velocity 0. In fact, if I wanted to know the velocity of this thing when it hit the ground, I would use, well, I know the velocity in x, it didn't change ever, it's 14 meters per second, and then I can use v equals v naught plus AT over here, and I could say, well, 0 plus negative 9.8 times 2.5, and I could come up with how fast it's going over here. And it would be about 25 meters per second. So it's actually falling fairly quickly when it hits the ground, but it's not at rest until after it hits the ground. So don't use that final velocity of 0. The only time the vertical velocity is 0 is when the ball is at its